So welcome to the fifth lecture of differentiation. So I think I am audible. Let me start. So today's talk, I will start with recalling the theorem that we did earlier. So recall the theorem. What theorem? I discussed the proof in the third class, most probably. Second or third. The theorem I am writing here. That the function such that. So that is the component. What is the function of the original derivative of original function in terms of the component function, such that f equal to fm, where fi is at r into d of fa. So it is a linear transformation, right? It is nothing but, oh sorry, first of all, f is differentiable a belongs to Rn if each fi is differentiable at a belongs to Rn. That is one thing. But most crucial thing is that thing. What is the transformation? Sorry. What is the matrix of the linear transformation? Or what is the linear transformation itself? So it is the tuple of the individual components. Okay. I only statement only. I am only recalling the statement only. So now this is if this is the thing, and then what is the Jacobian matrix? Jacobian matrix is ith row is fi dash. That we did. The matrix, so this is not arranged in this thing. This is arranged in such a way such that the first ith row is this. So mth row is this. Mth row consists of this. That not means that they are arranged by side. Actually, you can think that they are arranged by below. df1 is this, df2 is this, dfn is this. So that the fn, so the ith row of the Jacobian matrix. So one thing, let me write it here. So f dash a is Jacobian of f. So Jacobian will be f is a map from Rn to Rm. So f dash A will be a matrix of reverse m cross n. So there will be m rows. So the m rows will be, first row will be of f1 dash A, f second row f2 dash A, and mth row will be fm dash A. Sorry. So I mean, in particular, they are side by side means they are arranged below wise. That is the statement. Okay. So from the statement, I only know the drawback is I only know what is the row entries, what is the row about, what, but I cannot say what explicitly what is the ijth entry of the matrix. I cannot say from the data because nothing is mentioned. The what is mentioned is the what is the ith row, what is the first row, what is the second row. So there will be some. So it will. So fi dash t is a linear transformation. So I mean f1 first. Suppose f1 is from Rn to R. So the matrix of f1 dash a will be from 1% matrix. That is the first row. That is the first row. Similarly for f2 dash at a. That is the second row. It will be another 1% matrix. So there are m things are arranged here. So that will be an m cross n matrix that matches with the order. Okay, so you are arranging each the Jacobian of each particular linear transformation uh, from top to bottom, one above other. Okay, so in the following theorem, we will try to visualize what are the entries of the Jacobian matrix in terms of partial derivatives. Fine. So following theorem, we will find out the of the Jacobian matrix if test A in terms of d I or djfi in terms of various partial derivatives. So here comes our next theorem. What is the statement of the theorem? Right? Yeah. So it is a differentiable function. F equal to Fm, then each partial derivative of each component function. So in short, I can write dj fia exists each one I m, because there are m functions, say n, because there are n variables. M test A, uh, m cross n matrix with entries dj f I a. Okay, that is the thing that we need to prove. So you understand the statement, what we need to prove. So let us look for any fi. Take any fi where 1 im. Okay, then fi is a map from Rn to R. We are defining a new function. Okay, same thing. What we have done, I mean, in the previous lecture, that when we are linking the partial derivative with a single variable derivative, we same function. This is the coordinate. Okay, A is this point. A, which is this thing. Okay, fine. So H is the that thing where there is an X in the jth place. Jth place. So that means we are able to find the jth partial derivative here. Then what is, we have already we have already studied this. What is this? This is nothing but this is, okay. Let me do it in the next line. Then dj fia, that is what? That is limit k tends to 0. So this is a big fraction. This is fi a to a j minus 1 will be fine till j minus 1. Then at j's place it will aj plus h, aj plus 1 dot 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 by definition minus this thing by k. Sorry, it will be k. So but we can replace this point by and this point in the next line by the suitable functions on of h, same k. That thing is nothing but if I compose h, h uh, ai plus k minus if I compose h, aj, sorry, it's jth position, right? So it will be aj. This, I mean aj plus k, aj plus k. It is not a of j, a suffix total j plus k, it is aj plus k. So this is this thing. This is this thing. Not this, that much line is needed. This limit k tends to 0. So it is single variable function in composite. So this is nothing but, okay, I don't need to even write. It is if I compose h dashed at a aj. That is the definition. Okay. That is the definition here. But by chain rule, by chain rule, just a minute. Which is equals to f of h a j whole dash h dash aj. This is by chain rule. But what is this? F of, so that means f of h a j, that means f a, I mean f dash k. Because h a j is a into h dash h. If I, if I, this k looks weird, I mean, this is same k. Fine. Now, this is a Jacobian matrix. This is also a Jacobian matrix. Remember, Fi was a map from Rn to R. So, Fi dash A will be a matrix of order reverse 1 cross n. So, let us assume that the matrix is this F 1 1. So, it is I. So intentionally I will name it if I1, if I2, if I1, if I2, if IN. Similarly, H. H is a matrix from what? Rn. H is a matrix from R to Rn. That means H dash Aj is a matrix of order n cross 1. It is a column vector. I have to say remember. Now what is H dash of Aj? So let me write it, okay, first. This is I1, I2. I have in that thing. Okay. And H dash Aj, I know the structure of H. What? This is this thing. So if I do the original derivative and put this, what will be this? This will be, so it is a matrix, okay? So this place will be 1 and 0. Putting x will not, will not hamper, will not change because there is x, so derivative will be 1 and this portion derivative will be 0 because it is again some tuple. This is again, some tuple, so individually differentiating over all tuples. You are differentiating all tuples. Okay, just a minute. Yeah, you are individually differentiating the tuples here. And from that formula, from that thing, f is a function from Rn to Rm. So that thing will be df1 and df2. That thing I told earlier. First column will be the component of the first derivative. Second row will be the second row will be the second derivative component. In this thing, first derivative will be 0. So the jth position will be 1. Every other thing will be 0. At the start of the theorem, what I told. So this will be 0. This will be at jth position. What is this? If you multiply, you will get it is 1 cross n, it is n cross 1. So you will get a only scalar, f I j. Understand? So let me check whether, uh, f I j is actually, f I j is, that is the, I mean, this thing. This is not f I j. So if I rename, so if you have written, don't need to erase, otherwise you might erase it. So if it is this thing, if you rename this way, you will understand it better. In A. Then you will understand better. Okay. So then I don't need to write it. It will be if I j test. So what was this thing? This is actually this thing. But this thing always exists in this column. Because if I is there is some entry which is this, the jth entry. That exists. So that also exists, which I need to show. The first thing. So I need to show first this exists. So this exists as I and j are arbitrary. I mean, I can control this thing. I mean, this is not vanishing. I can put the value, whatever it is. This is not 5, this is not 1, this is not undefined. This exists as it. I say arbitrary, arbitrary plus gz if I a exists. The existence part is clear, right? So existence part is clear. Now how to show about the matrix is this. See, what is your best? The Jacobian matrix of f dash, which is f dash a, is an m cross n matrix. So there will be, I mean, according to my notation, that is f1 dash a, f1 2 dash a, dot f1 n dash a. The last row it will be, okay, in the second row what it will be? It will be f2 dash a, f2 a dash f2 n dash a. This is according to our notation. Last row, it will be if m1 dash a, if m2 dash a, dot, if mn dash a. This is the Jacobian matrix because we denoted the ith linear ith row according to this, the ith Jacobian matrix. So in full form, the Jacobian matrix is this, but this thing, whatever you element select, the ith element is actually this that we prove. So I can replace this thing by this. Where? Here. So that is nothing but this is nothing but so 1 a. Okay. So if ij is dji. Okay. So it will be d 1 f dot d n1. So in this way, I am not writing the second one, and I will write finally the first one. Last one. It is d1n d. The concept is clear, I think now. ijth entry is dji. It is reverse. Keep in mind. Okay. So this is the proof. I can finally replace this by this. So I think you understood the theorem, but the converse of the problem is not, the theorem is not always correct. So the converse is not correct. However, if we add one condition, when, what was the theorem? Yeah, our theorem was this theorem. This exists. Okay, if f is differentiable, then this exists. That was the main theorem. This is another thing. But if converse, if they exist, then the original function is differentiable. That is that is a natural question to ask. Okay. So in general, the answer is false. We will I will show later why it is false. But when it is true, one condition you need to add. The partial derivatives are continuous in some open neighborhood of the point. Okay. So I want to write the theorem first. This says that f is a function Rn to Rm. Just a minute. F is defined from Rn to Rm. A is a point of Rn. Then d of fa exists if all of the partial derivatives function exists, that is djfi x exists open set containing a. A is a point, okay, and they are continuous. Each of them discuss that. I need to show this. I need to show they are, if the partial derivatives exist and they are continuous in an open set containing a, then I can say that DFA exists. Okay. So I mean I only need to check when the partial m equal to 1. So we will check first for all component function. Okay. Fi. if I is known, then I can arrange fi to get f. So that's f is a function from Rm to R1. That means R. Okay. My target is to follow. Apply mean value theorem here. Okay. Is a plus h minus fa. This is obviously this thing. H is now this thing. So the thing is that it is what is a1 h1? It is a1 plus h1, a2 plus h2, dot dot dot, an plus hn minus f a1 dot 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 an. This is the vector. Okay, so why I am worried for m equal to 1 only? Because if m equal to 1, then d of a, I can show the d of fia exists. Now we know that d of fa is nothing but the row vectors. They're arranged in this manner. So to show that this exists, it is sufficient to show this exists. But d of these things, fi for each I is a mapping from R to R. Okay, because then I can, in place of f, I can assume fi, and f is just d of fa is just a tuple or a convect. That is just a, in a matrix form they're arranged. You understand what I'm saying? Okay, now plus and minus some quantity, same quantity. Then this is equals to, I am adding and subtracting same quantity. Okay. First of all, everything is fine. Now I am subtracting this plus you're understanding, right? These two will cross off. So inductively doing this, I am the last one will be I think this thing, the final one. Oh, sorry, this is the thing. By mean value theorem, first of all take the first two, these two. So sorry, these two. So the only increment is this position. So it is something like di of f, the first derivative of f into something. What is the mean value theorem? Okay, I am writing. What is this thing? it is A2. This is nothing but H1 into D1 because the first position the derivative is counting, so it will be D1. First D1 A2 AN or some D1 A2. Now do this all everywhere. In this last step, this will be an plus hn, so it should be bn will come. So doing this in general gives f a1 h1 a I plus hi ai plus 1. So let me write in the next line. If a1 plus h1 ai plus hi ai an plus a1 plus h1 ai minus 1 plus hi minus 1 ai. So it is ai plus 1, right? It is ai an. So it will give you something like hi ti fci. You can roughly assume ci c1 or c1 is this. In this manner, this point doesn't count, so it is c1. So there will be some point, okay? Some ci. So that much I am getting. So I need to show that what is my target. My target is to show DFA exists. DFA exists. That means DFIA exists. Okay. So arrange the required things. Now, what is this thing? The in the above there is f a plus h minus f a minus summation di f a into h I goes to 1 to n by norm of h limit h tends to 0. This limit. What is this limit? I can put the value. I can put the value of a plus h minus ah, that is limit h tends to 0 summation of t I fci minus di f a h I. Obviously, this is this thing divided by h. Why? Because of this. Because see, this part is this. So from the second part, I will get some h2 d2 f on some c2. Some third part I will get h3. But they are in sum. This is the first part. This is the second part. This is the last part. They are in sum. Okay. So it will be this thing, and I have taken in common. I have taken them common, and there is a bracket. So this summation I equal, and this is the thing. So I can now apply this thing to keep the summation out of the modulus sign, and I will get that will be, oh, summation this part into mod of hi by h. Fine. But see, this is less than equal to 1. There is, because mod h is, I mean, this is h1 square plus hn square. How many h are there? So as many h as there, this is that much square, sum of the squares, and take the square root. So I can do this. This is the bounded above by this thing. There will be one. There will be modulus Cn minus Ui. The thing, and this is 0. Why this is 0? Because we assume, why is the theorem? DIFI we assume to be exist, and they are continuous. That they are continuous at A. That means we can, this is 0, this is 0. So I am writing okay. Therefore, this limit is 0, and our claim is established. So I can go with I. So D of Fi at A exists. As soon as that exists, D of Fa exists, because this is the D of F1A, comma, D of F2A, comma, D of F3A. Okay. So this is done. So the last thing theorem, it is easy corollary. It is the about the Jacobian matrix of the what I have said of the differentiation. My theorem is, let G1 to Gn every be continuously differentiable. So what is continuously differentiable function? It is this thing. If the partial derivatives, so I need to write it here. It is the definition. Continuously differentiable means what? Every partial derivative of every component function will exist, and each of the partial derivative of each of component function are continuous at some open neighborhood of that point. So my point is that if they are continuously differentiable, at the again that if Rm to R differentiable at this thing. So it is a m tuple function. So it will input a m value, m tuple value. So this is a point. Each point lying between in R in real numbers. So this tuple is a tuple in Rm. So f can input the value and output something in R. Then define f R power n to R by fx is f of the composite function of f. Then what is the DIF? Partial derivative. Okay. It is very trivial corollary, you can say. This is j equal to 1 to m j if this into di j. Again, I am saying these are all written in Spivak's books, Michael Spivak. The book name is Calculus on Manifolds. Okay. So let me prove this first. This is the last theorem. So to solve this problem, I will define a new function. So let us define G is a function from R to Rn by G of X is job. Yeah. So it is A, this thing. So what is F? So this implies F is F compose C. Sorry, it is X. They are X. So this thing gives us F is a composite function of F compose Gx. So now, so we need to determine what is this. For this, we need to determine what is the differential matrix. What is the differential matrix, or what is the Jacobian of differentiation of A. See, one thing is guaranteed. As GI, GI is continuously differentiable at A by this theorem, where it says that if the component function are continuously differentiable at some open set containing A, then the original function is differentiable. Then the original function is differentiable and this exists. So apply the same thing for G. So they are continuously differentiable at A. Thus, previous theorem, we can say that G is differentiable. Okay. So by chain rule, of differentiation, what are we getting? We are getting if test A. So this is some entry of the this thing. This thing is some entry or some row or some column or whatever you say. This is some entry of the the Jacobian matrix of differentiation of A. So unless we determine this things, f dash A, we cannot say what is this actually. So what is f dash A? It is by chain rule. It is f compose G of A whole thing dashed. That means it is equals to f of G A this dashed into G dashed A. Fine. But see, f is a matrix, f is a function from where to where? F is a small f, Rm to R. So that will be of 1 cross n, the differentiation matrix. And you already know what are the entries now. That is D1 F of GA dot DM F of GA. Because by this theorem we know, and also G is a map from G test, right? G is a map from Rn to Rm. So G is a map from Rn to Rm. So the matrix representation of G test will be M cross N order matrix. So what is the entries? We know from the previous theorem again. So they are P1, G1A, G1A. That is 1 comma nth entry, but it will be reverse. It will be NA, DN G1. Again, it will be M comma 1, but it will be reverse. D1 GMA. It is not DMG1A. Similarly, it will be DN. Fine. So if we can now multiply them, no need to give comma, to be honest. Now, if we multiply them, then we will get another matrix. So now what is this? What about this? This is something like DIFA, D2FA, then DNFA. So comparing, see, this is also a matrix, right? This is also a matrix. Comparing the sides. Okay. It is D1FA. Sorry, DIFA. And how the ith entry here is generated? You need to multiply them with the ith column. That means it is exactly what we are getting, say equal to 1 to m d j f of g a into the corresponding these things d I g j a. Actually, you can, what is GA? Now put the value of GA. GA is so if we write it properly, then it will be J1 to M, DJ will be DJ, and this will be F of G1A, GMA multiplied by DI, DJ. This is the comparing. First apply chain rule plus entries of matrix, then compare. Nothing but this. So this is the our this we needed to prove here. That is proved. So I want to conclude my class here now. Thank you.